Good morning, sir.
Hmm.
Sir, Good morning, children. Today we will try to understand a different law. Yesterday we have seen Gauss's theorem, Gauss's law, and its application. I hope you have learned everything about current electricity. Today we will discuss one of the very important concept in current electricity. It is nothing but Kirchhoff's laws. Kirchhoff's law we use when we are not able to use Ohm's law equations in some complicated circuits. So such cases we use Kirchhoff's law for solving a circuit to find out the current in the circuit, potential difference in the circuit, etc. So the very important law in current electricity is Kirchhoff's law. Let us start understanding this law very clearly. So Kirchhoff's law, we have two laws are there. First law is also known as current law, or it is also known as junction rule. Current law or junction rule. So this law is one of the very important laws in current electricity. Kirchhoff's law. He found this law or used this law to find out electric current in the circuit, a complicated circuit where we are not able to use Ohm's law, which is very familiar to you, Ohm's law. When we are having voltage and current and resistance in the circuit, we use that law, or V is proportional to I, a very common law, we use that. But in certain cases, we are not able to understand clearly or distinguish between parallel circuits and series circuits, series part of the circuit. So such cases, we are not able to identify which all the resistance are in parallel, which all the resistance are in series. Such cases, we can use Kirchhoff's law to solve such kind of circuits. So it is mainly known as junction rule or current law. So we can just we'll see one junction. It is in a network, or the algebraic. We can say the statement like this: algebraic sum of currents at a junction in a network is equal to 0. Algebraic sum of currents at a junction in a network is equal to 0. This is what we call the current law or junction rule. This is applied to a junction in a network. So in a network, if you have currents coming towards the junction, or some currents will be going away from the junction, but we can say that total current, algebraic sum of the current at a junction is equal to 0. Or we can mathematically you can write that sum of currents is equal to sigma I is equal to 0. We can write. So let us see how it works in a circuit. Okay. So in a circuit, suppose I am going to put a circuit here. So a junction, in fact. So we have this is a junction and different current coming over there. So we can say that so this is I1, this is I2. This is I3, this is I4, and this is I5. Okay. Now some of the currents are coming to us, some are going away from this. So we have 1, 2, 3 currents coming towards the junction, and two currents are going away from the junction. So how do we write a statement equation or mathematical equation for this using current law or the first law or junction rule? So we have to what do you mean by algebraic sum? So means the total current at a junction is equal to 0. Means we can we have to assume sign convention. Sign convention means we have to give some sign. So algebraic sum means some will be positive and some will be negative. So such cases, what we can use the current coming towards the junction, we assume that is positive. So we can say that current coming towards the junction is first taken as positive, and current away from the junction is taken as negative. So two sign convention we take. So this is current towards junction, coming towards the junction is positive, current going away from the junction is taken as negative. So these are the two convenient sign convention. We can say that the charges, so current is nothing but flow charge with respect to time. Now we can say that all the charges flowing in is an addition to that junction. So we say that it is positive sign we give, and again current is going away means charges are flowing out. So those charges coming out of junction is taken as negative. So what do we do with this equation now? So you have taken the statement, this algebraic sum of currents at a junction in a network is equal to 0, right? Or simple, you can remember that current sigma I is equal to 0. Simple way you can say that. So the first law we will see how the equation, how can you make the equation for that. So equation you can make, right? So I1, I told that current towards junction is positive. So which are the current coming towards junction? That is I1, I2 and I4. So we say that I1 plus I2 plus I4, okay, minus I3 is going away, I5 is, so minus I3 minus I5 is equal to 0. So this is the equation we can say I1 plus I2 plus I4 minus I3 minus I5. Or we can say that I1 plus I2 plus I4 is equal to I3 plus I5. Means current coming to a junction is equal to current going away from the junction. Means what we mean by this statement is that no charges is residing at a junction, no current is staying at the junction. Or we can say that it follows the law of conservation of charges. Okay, this law or the first law or junction rule or the current law is in accordance with the law of conservation of charge, which says that no charge can be created or destroyed, or no charge can be accumulated at one place. It will be either distributed out or it's coming in. So that is conservation of charge. So total charge coming to the junction is equal to total charge going out of the junction. No charge is going to stay at a point in a network. So how do we prove that case also? How can you say that the charge not reside? How it is conservation of charges? Means you have to say that Q1 plus Q2 plus Q4 is equal to Q3 plus Q5. Is it possible? Okay, is it possible? And then we just simplify this equation to prove that this law follows the law of conservation of charges. Okay, so means charge not accumulating or residing in a junction in a network. Now what we do is to prove that case, we can divide both what we call what is charge is equal to Q is equal to I into T. Okay, so we can say that this Q1 plus Q2 plus Q4 is equal to Q3 plus Q5. So we can multiply both the sides by T. So we can simplify that. So I1 into T, or I2 into T, I4 into T, and I3 into T, and I5 into T. So we multiply this by T, we can do that both the sides. So this I1 into T, so we can say Q1 plus Q2 plus Q4 is equal to Q3 plus Q. So we can say that the total charge coming towards the junction is equal to total charge going out of the junction. Means net charge at a point is equal to 0. So this shows that the Kirchhoff's first law follows law of conservation of energy, conservation of charges. So again, I will explain once more. The first law is a current law, total algebraic sum of the current at the junction in a network is equal to 0, or the current, we follow the sign convention for finding the algebraic sum. So the current towards the junction is taken as positive, current going away from the junction is taken as negative. So when you give the signs for the current coming towards and going away, so we can get I1, which is coming towards junction, positive, I2 positive, I4 positive, minus I3 minus I5 is equal to 0, or we can say total current coming to the junction is equal to total current going away from the junction. So this is Kirchhoff's law or junction rule. Let us understand this with a simple problem. So let us see a part of a big circuit. So we can find out the current in the circuit. So it is not, we cannot easily find out which is parallel, which is series in this kind of circuit. So this, we can say that at this part, a 10 ampere current is coming here, and 1 ampere current coming here. Now from this, we take an 8 ampere going there. So this is your I1, this is I2, this is I3, this is I4, and a 6. So current I1, I2. So we want to find out I1, I2, and I3. Okay. So to find current in each branch of the circuit. So there we have 1, 2, 3, 4, 5 junctions are there, right? So we want to find out I1 is equal to how much, I2 is equal to how much, I3 is equal to how much, I4 is equal to how much. So we cannot use here because no potential difference is given, resistance is not given. So how do you find current? We cannot use Ohm's law. So straight away we have to use the Kirchhoff's law junction rule here. Now, for example, how do we find it? Now here, 8 ampere current coming, 10 ampere current coming here. 8 ampere is going this way. So how much will be here? This is 2 ampere, right? We can get 2 ampere current, and from here, suppose you take 1 ampere current. We assume that there is current in this branch, 1 ampere current. So what? How much will be there? So out of this 2 ampere, 1 ampere is leaving this side, or 0.5 we take, 0.5 ampere, 0.5 ampere. So 2 ampere is coming at this junction, 0.5 ampere is leaving. So how much is remaining here is 1.5 ampere. So we got current along this is 1.5 ampere. And here 0.5 ampere is coming and 1 ampere is coming here. So how much will be there at the junction? So the remaining current will go to 2 currents are coming to the junction. So that is 1 ampere plus 0.5 ampere. So here again we'll get 1.5 ampere coming because 1 ampere is coming on this side plus this 0.5 ampere. So both should come together and flow along this direction, that is 1.5 ampere. And here at this junction 8 ampere is going this side. So out of that 6 ampere is going along this direction. How much is the remaining there? So 8 minus 6, that is 2 ampere will be here, right? And 6 ampere out of that 1.5 ampere is going this side. So how much you will get here? 6 minus 1.5. So that is 4.5. So this is the total current in each branch of this. So we can, this depends on the resistance. Whatever resistance in the circuit, the value will change. So we will get, we can easily find out the current at junction is equal to 0. That is why we could solve this kind of problem. So there we will get the current I1 is equal to 4.5 ampere, and this is I2 is equal to 2 ampere, and this is 1.5 ampere. This is also 1.5 ampere. So very easily, without much calculation, without using any equation, we could solve this problem very easily because of Kirchhoff's junction rule. Means total current coming towards the junction is equal to total current going away from the junction, or simple way, sigma I is equal to 0, or net current at the junction is equal to 0. Means it is clearly following law of conservation of charges. Very easily we can say that no charge is residing at a junction in a network where current is flowing. I think it is, I hope it is clear about the Kirchhoff's first law, junction rule. We can use any kind of problem. So this will be used in any network to find out the current. Okay. Now another rule, another law, Kirchhoff's law is there. So that law, which is also known as voltage law, this current law, and second law is, we wrote it down. Right. So second law is, Kirchhoff's second law is known as loop rule or voltage law. We can say that loop rule. It is only used for a closed circuit. Okay, so a closed circuit, you have to take a closed circuit, then only we can, so a completed circuit, a closed circuit where current is flowing through a network. So such kind of circuit we use a loop rule to solve current in the circuit. So what do you mean by loop rule? Which says that algebraic sum of the voltage drop or algebraic sum of potential drop. You can say that potential drops is equal to algebraic sum of EMF. So that is algebraic sum of the potential drops in a circuit is equal to algebraic sum of EMFs. So some circuit we will connect EMF, or the cell will be connected providing current, or potential difference is we can establish potential difference only with the connection of cells, so that we can give potential difference. So what is potential difference after all? It is nothing but work done to move the charge or move electrons in a circuit from one point to another point. So work done is nothing but energy. So it will be energy will be provided by the cell, and energy will be consumed by the resistors in the circuit. Okay. So algebraic sum of potential drops. So potential drops will come only when there is a resistance in the circuit. So any branch, any resistance, each and every resistance. So we can say that this potential drop is provided by each resistors connected. Okay. Each resistors will be each resistors will be consuming that electricity, or it will be dropping its potential. So the potential drop will be there, or across it. So potential, we can say that 5 resistance on the circuit. So each one will have a potential drop, or potential difference will be there. So such cases, total algebraic sum of potential drop is equal to algebraic sum of EMFs in the circuit. So how do we express in mathematical form there? Or we can say that in a simple way, sigma B is equal to 0. That is final value. So sigma B is equal to 0. So, or we can say that the algebraic sum of potential drops is equal to algebraic sum of EMFs. So how do we make a circuit for this? So suppose you have a closed circuit. Okay. So this is a closed circuit. So closed circuit in the sense there is no loss of current anywhere. So there this is E1 and this is E2. Now, so we have to decide which part of the circuit is a closed circuit. Okay, so we have to take. We can give the name. So this is A, B, C, D, E, F. Suppose this is 2 volt. This is 6 volt. Assigned to this R1, R2, and R3 we are given. Now, first we have to give a direction, arbitrary direction. So we know that the current always starts from the voltage in the cell. So 6 volt is dominating 2 volts. So direction can be taken like this. So always start giving direction from the higher voltage side. So there is not compulsory, but it is preferably good to do that, because some cases we get negative current. The answer may be correct, but sometimes you will have some doubt whether it is correct or not. Right. So 6 volt, and from this junction here also the current is coming, and we can say that this current passing through, both coming here and here, the current goes this way and this way. So this assigning direction is also important. So we can assume that the current is going this way and coming this way also. There's nothing wrong in it. So if the current going the junction coming here and going this side, and so there is nothing wrong. So you can take your own direction, and 6 volt providing current here and going through this. So we have to take those. The loop rule is only for the closed circuit. Remember, It is potential drop in each resistor in a closed circuit. So our loop rule is equal to algebraic sum of EMFs connected. So we have E2 EMF there. So we take any. So how many closed circuit we can say? We can say that. So one closed circuit is A, B, D, E, A. Remember always you start with A, should be ending with A. So always remember that. It's a closed circuit. A, B, D, E, A is one closed circuit. And another one can be A, B, C, F, A. Right? So this is another closed circuit. Another one will be third circuit is, so you can start from anywhere. Suppose we start from E. So E, F, C, D, E. So we have three closed circuits are there. So we have to analyze, or we can equation. So using this Kirchhoff's second law, we frame equation for that, in which algebraic sum of potential drops in each across each resistance is equal to algebraic sum of EMFs. Now, how do we give algebraic sums? Means there will be some positive value, some negative value. For that, we need to have to provide sign convention for that. Now we have to take, now this direction what we have taken is our own will we have taken. It is not, so some case it will be clockwise, some case it will be anti-clockwise. So means suppose you are taken A, B, D, E, A. So you start from here. So we have taken a circuit like this. So this is one direction, and you have taken against the current, we say, or A, B, C, F, A. Okay, so A, B, C, F, A is this one, and A, B, D, E, F, A also we have taken starting from A coming towards this. So this also a bigger circuit. So like this, and E, F, C, D, E. So E, F like this you have taken. So this will be taken like this. So there is not to hesitate giving this arrow mark, because arrow marks will give you a clear idea which direction you have taken. So there is nothing wrong in question paper itself. You can make this mark arrow mark clockwise or anti-clockwise, what direction. So this is your freedom to take which direction. It is not compulsory to start this direction. You can start from B, A, F, C, B can be taken, or C, D, E, F, C can be taken. Anything can be taken. It should be a closed circuit. That's all. But remember always which direction you have taken while understanding or solving the problem. So is it understood now how to take a closed circuit? Now the direction of the potential drops or current and algebraic sum of EMF. So we can take, so we have a left hand side, we have a right hand side. LHS is equal to RHS. Right. So how do we decide this? What sign to be given? So if you are taken your arbitrary direction in the direction of the current, if you have taken arbitrary direction in the direction of current, then you will give positive value for the potential drop. Otherwise, if you have taken direction or your own arbitrary direction, what you have taken is opposite to the direction of current flow, then you will take it as negative. Understand? If you are moving in the circuit, or you have taken a direction in the circuit, or you have taken A, B, D, E, A. So we have decided the direction. If that direction is taken against the current flow, which already we have decided the current flow, then it will be taken negative value. And if you have taken again in the direction of current, it will be taken positive value. Understood? This is clear, because that if any mistake in giving sign, the algebraic sum will be wrong or problem will be wrong. Again, I will tell you, if you have taken a direction in the same direction of current flow, okay, a circuit clockwise direction or anti-clockwise direction you have taken, in the direction of current if you have taken, then give positive value for the potential drop, or in case if you have taken opposite to the direction of current, then you take negative value for that. And similarly, RHS is the EMF also. When you are taking a current flow, when you are entering the circuit through negative terminal. Okay, so if you are entering a cell through the negative terminal, so you give it positive value because it is coming out through the positive direction. Or if you are entering in a cell through the positive terminal, then you will give it as negative. Is that clear? So if you are entering a cell through a negative terminal, take it as positive, and if entering through a positive terminal, take it as negative. So that is the sign convention we are going to give. So let us solve one equation. So we have to make your equations here, any number of equations we can take, because three circuits, closed circuit is there. All the three we can make equations, and we can using this LHS and RHS formula. So let us start with first equation, A, B, D, E, A. So A, B, D, E, A. So the resistances are there. So we have here there is one cell. Here nothing is there, and here nothing is there. Here one resistance there. So what is the value? So you are taken in this direction. So you are moving against the direction of current flow. So what we do is, what is the current? We will give current also. This is I1, this is I2. Okay. So here we assume that I1 plus I2 coming here. It is assumption, so we can change. Suppose you are taking I3 also, we can put. There is no problem. So I1, this I1 is in this branch, so we can say the equation. So that is I1 into R3. I1 into R3. So what sign we give? So because we are going against the direction, so here it is coming this in the direction of the current. So here it is coming in the direction. So current is flowing in this direction. So we are moving in the direction I1 into R3 plus or minus. So here it is against the direction of current. So this circuit, here current is this flow, this direction. So you are moving against the direction. So what is the current here? I2 current coming here. So we can say that minus I2R1, right? So two resistors were there. So R3 is one resistor, R1 is another. So we have taken A, B, D, E, A. So in this direction of current, we have chosen in this direction. So we take it as positive value. So I1, R3. I1 is the current, R3 resistance, minus, because why minus taken? Because you are going against the current. So that is I2, R1 is equal to, now right hand side we have to get the EMF value. So when you are starting from here, we are entering through a positive terminal. So what we give there? Minus. So minus even. So we are entering through a positive terminal, you minus value. Now here you are entering through a negative terminal. What will give? Positive. Okay. So this E1 is, we have assumed that E1 is 2 volt minus plus 6 volt. So that is 4 volt. Right. So we can say that I1 R3 minus I2 R1 is equal to 4 volt. So this is one equation you can say. And we know that to find the current in the circuit, any equations, it is variable. I1 and R1 and R2 will be given to you because it is a resistance given to you. And we can note down the resistor, and or if a carbon resistor, you can measure the values in calculating case, or it will be given to you. So I1 and the two variables are there. So here we have two variables. So when two variables are there, we need to make two equations to solve I1 and I2. So second, this is first part, first equation we got, and second equation, what we have taken is A, B, C, F, A. So how to make an equation for that? How to make equation for the second one? A, B, C, F, A. This is one equation. So we start with A, and this is against the current again coming. So that is minus. What is the current here? I1 plus I2. So that is I1 plus I2. I1 plus I2 into R2, right? So I1 plus I2 into R2. So this is, we are coming from A, B, C, F, A. So against the current we are moving. So therefore I1 plus I2 into R2. So then one more resistor coming here. So that is also against the current. That is minus I2 R1. Okay, minus I2 R1. So that is equal to, how many cells are there? Only one cell. So we are entering through a positive terminal, give the value minus 2. So this is the second equation. So you got two equations there. So I1 plus I2 into R2 minus I1 R1 is equal to minus 2. So this is one of the simplest way we can use this, and there are so many different sign convention provided. At the end, all the equations will be same for the convenience. So this will be, or we can algebraic sum of, some cases will be given, some books will be given that total potential drops is equal to 0. Means this will come here, then all this will become, change the sign and put this side, or we can say the sum of voltage is equal to 0, but potentials are 0. So that way also, but this will be more convenient and easy to remember. So let LHS equal to RHS, so you can make equation easily. Means algebraic sum of potential drops in each part of the circuit, each resistance. So that will be equal to algebraic sum of EMF. And this law is mainly follows the law of conservation of energy. And it's conservation of, what is the conservation of energy? Energy can neither be created nor destroyed. So first law we have seen the conservation of charge. Now here it is conservation of energy. So how do you say that it follows conservation of energy? Because any part of the circuit, we can say something, there is a cell provided, a cell is providing energy. Okay, potential drop is what we call potential drop. Again, the basic understanding is the amount of work done to move the charge from one point to another point. Suppose we take E and D as the 2 points we have taken. So the work done to move the charge is potential difference. So who is providing potential difference here is cell. If cell is not connected to the circuit, you don't have a potential difference, right? So when you are considering the cell, a potential difference is provided by that. So the energy provided by that, and when current is passing through a resistor, it will be a potential drop, a use of energy there consumes, and the resistance will consume energy. We know that the current is passing through resistors. Some cases heat will be provided, some cases light will be provided, whatever way it consumes energy. So there is a drop in potential. So in the sense, total energy given by the cell and consumed by the resistor will be same, means it will be balanced, or we can say conservation of energy. Anywhere, any circuit, in part of the circuit, we can say that the energy conservation is taking place, so energy created, no energy not created, nor this will be converted from one point to another point. So first law, or the junction rule, follows the law of conservation of charges, and second law is giving you law of conservation of energy. The first law which says that the total current at a junction is equal to 0, or algebraic sum of current at a junction is equal to 0, or we can say that the total algebraic sum of current coming to the junction is equal to the sum of current going away from the junction, or algebraic sum of total current at the junction of a network is equal to 0. That is a part of circuit. Now here the loop rule, which is giving you very clear idea about a closed circuit only. So it will be only used for a closed circuit where we are not able to identify. Suppose we want to find out which is parallel and series. So some cases it will be followed, some cases it will not be followed. So such cases we have to identify the Kirchhoff's law to use in different circuit. This is used for closed circuit. Accordingly, the algebraic sum of potential drops in each part of the circuit is equal to algebraic sum of EMFs in the circuit, right? So let us try to solve one problem and try to understand how to solve problem using this Kirchhoff's law. Already we have seen junction rule, how to solve problem. Now here also we can try solving a problem. So this is a circuit. We can give name for the circuit. A, B, C, D, E, F. Now we can take the direction of current. So we can take direction of current. Suppose I1 amount of current here is coming here and it's going this way. And if you take the current coming this, you can take this, no problem. Or you can take current coming from 4 volt and going away. And this is one, you have taken current here. So some current will go there and the remaining will, this is coming here and going back. So the direction we have taken. So direction is to be given. So it is not necessary that your direction of current is always correct. Some cases, when the answer will be negative, then you can say that the direction taken is wrongly taken, the current in a different way. So there is nothing, no mistake in that. So we have taken I1 current coming from this side, and this I2 going this way, right? And how much will be there? I1 minus I2, right? So don't take I3. So I3 means again one more equation you have to make. So try to reduce the time when solving problem and all. So if you are taking I3 here, again one more equation you have to solve 3 equations differently. But here I1, I2 will go there, remaining current I1 minus I2 will go through this way. And of course, here I1 will be there because coming back, and here I2, and this will be I1 minus I2. Means when I'm taking I2 here, so this I1 is equal to junction rule. Here we can follow that I2 and I1 minus I2 coming towards junction, right? So we can say that so this is nothing but I2 plus I1 minus I2, right? So we will get I1 there. So I1 back, because that one current is starting from 10 volt, the same amount of current should come back to the same point. So here junction rule, in case you want, you can use the junction rule. So that's I1 is equal to I2 plus I1 minus I2. So that clear? So how to give the direction and how to make equations now. Let us see how to make equation there. So we can make two equation minimum we require. Okay, so we take one equation which is AFCPA we take. Okay, that is AFCBA. So this is for this equation. We get AFCBA. Now you start from here. I1 amount of current coming at this point. So what is the equation in the direction of current? So sign convention will be taken a positive value. So that is I1 3I1 you can see. So 3I1, that is positive value. Again, current is coming in the direction of your direction. So you have taken AF. Sorry, we have taken AF. No, so this is your direction. Mark the direction will be easy to understand. So AFCBA we have taken. So this is the clockwise direction we have taken. So 3I1, then 2 ohm resistance there. So that is again in the direction plus 2I2, right? And there is no more resistance there. So that is equal to, where is the current entering through negative terminal? We take it is positive value. So entering through positive negative terminal, that is 10. So we got one equation which is 3I1 plus 2I2 is equal to 10. And another equation we can take, for example, this bigger circuit we can take. So that is F A E D B A. Okay. So this equation for A E D B A. So there you will see again equations. So that is 3I1 plus value, and here there is a resistance again in the same direction. So that is plus, what is the current there? I1 minus I2. So that is plus 1 into I1 minus I2, right? So 3I1 plus 1I1 minus I2, right? And that there is no more resistor in the circuit. So, but you have two cells coming. Now, when you start from A, so we start from A, so you are entering through a positive terminal. So we take it as negative value minus 4 volt, and here we are entering through the negative terminal, so that will be plus 10 volt. Okay, so this is the second equation. Now simplify this, so that is 3I1 plus I1 minus I2 is equal to 6, or we can say that 4I1, right, minus I2 is equal to 6. So this is your equation 2. You can say this is equation 2. So equation 2 is 4I1 minus I2 is equal to 6 volt. So we want to find out I1, I2, I3. How do we find the three variables there? Current of I1, I2, and I3. How do you find this? You're using the two equations. We have two equations there. So that is 3I1 plus 2I2 is equal to 10, and similarly 4I1 minus I2 is equal to 6, right? So two equations we got, that is 3I1 plus 2I2 is equal to 10, and 4I1 minus I2 is equal to 6. So how do we solve this? Eliminating some terms. So suppose you multiply this by 2, right? This into 2. So the equation 3I1 plus 2I2 is equal to 10. Multiplying this by 2, so you get 8I1 minus 2I2 is equal to 12. Okay, adding these two, what will get? 11I1, this cancels, is equal to, right? And I1 is equal to 22 by 11. So I1 is 2 ampere, and give the value for I1 in any one of the equation, you will get I2 also. Suppose in this equation you give, so what you will get I1, 3I1, that is 3 into 2, that is 6, plus 2I2 is equal to 10, or 6 plus 2I2 is equal to 10, or 2I2 is equal to 10 minus 6 is equal to 4. So I2 is equal to 4 by 2. So we get this value of current, both the current there. So we can solve the equation there. So this I2 coming this way and I2 coming this way. So I1 minus I2. So you can get, in fact, the current according to this equation. You can solve the equation there. So the equation for current in any closed circuit, we can get the equation very easily. So this law, which is giving you the law of conservation of energy, law of conservation of energy, or law of conservation of charge. In first rule, we have seen that law of conservation of charge, and second rule, we have seen law of conservation of energy. Now, this equation or this rule we have used for different purposes. We use certain devices like what you call meter bits or potentiometer, or the different devices are there. So in practical classes, we will do those experiments based on these equations. So this principle of Kirchhoff's law, we can use it very easily so that we can solve the problems, or we can find the unknown value. So one of those devices, what we call meter bridge. So based on a principle, what we call Wheatstone principle. Okay. So it's application of Kirchhoff's law. So where do we apply this Kirchhoff's law is Wheatstone bridge. So Wheatstone bridge is nothing but the arrangement of four resistances like this. And there is potential difference given, and there is a galvanometer connected across. So this is P, Q, R. So this one of this will be a known value. So suppose P, Q, and R is known to us. We can find the S value, which is unknown. One of this can be variable resistor also. We can adjust the value. So the Wheatstone principle says that when current passing through the galvanometer, so this is a galvanometer. Now suppose this is I1 current coming here. So this is I2 going this way, and this is IG amount of current. And we can say that the remaining I1 minus IG is going through this, and of course here will be I2 plus IG, and coming here will be I1 plus I2. So this is the circuit we can give. So in this case, what Wheatstone's bridge or Wheatstone's principle says that we can adjust the variable resistor here so that we can increase or decrease the value, so that the current passing through IG or through galvanometer, which is IG, can be made zero. So when no deflection is coming on this galvanometer, it says that P by Q is equal to R by S. So P by Q is equal to R by S when IG is equal to 0. So this is possible by adjusting a resistor. There is a variable resistor rheostat which can be adjusted so that we can give a variable value. Accordingly, the current will change. Then the I1, I2, this or current can be changed. So therefore, we can find out a net value of current passing through galvanometer is 0, or it gives you 0 deflection. or we can say, suppose this is A, B, C, D. What we can say that the current is not passing through galvanometer. What does it mean? It means that there is no potential difference between B and the potential difference is zero. For the flow of current, we need a potential difference. Without potential difference, current will not flow. So this resistance adjusted in such a way that there is no potential difference between B and D, or B and D are having same potential. So therefore, if the condition is satisfied, if condition of current passing the galvanometer is zero, then we can say that V by Q is equal to R by S when this condition is satisfied, when IG is equal to 0. Okay, so this will be it. So this will be done in Keystone bit. So this is also can be used. You can find out I1, I2, I3, and all by using Kirchhoff's laws there. So I'm winding up here. So we have used two rules. We understood two rules or two laws. Kirchhoff's law. First law is junction rule. Second law is loop rule. Loop rule is always used only for the closed circuit, and junction rule is for at junction at a network. So junction rule follows law of conservation of charges, and loop rule follows the law of conservation of energy. Okay, so both these rule will be used when you are not able to solve equation by using Ohm's law. A complicated circuit, we use equations to solve equation and find the current in the circuit or potential difference in the circuit. Anything can be found. Thank you.